Hello. So today we have the logic quiz assigned. So we're going to have one video today to cover new probability content. But please, if you haven't done so already, check out the logic quiz. It's not very long. I think it'll take you about half an hour to go through and maybe another 15 minutes to download, type up, and upload your solutions. That is due 8 a.m. Next day. So please do that first. But other than that, let's jump into today's probability topic. It's on Russian roulette, or slightly different versions of Russian roulette. Let's jump in. Okay, so Russian roulette is played with a 6-shooter revolver. So your chamber for bullets might look something like this. And then what we'll do is we'll stuff in 2 bullets in consecutive chambers and spin it. And what the revolver will do is that wherever it stops spinning, so there's 6 possible spots. Okay, whichever chamber that comes to the top after it spins, it will try to fire that chamber. If there's a bullet in it, it will fire. If there isn't, then it will shoot a blank, and then it will rotate 1 spot to the next spot. Okay, so as if that's already not dangerously enough, what we'll do is we'll pull the trigger twice. But you have a choice. Maybe you want to pull the trigger twice in a row. So you will see maybe it lands here and then there's no bullet, so you survive. And then the next chamber will also miss. Or maybe what you could do is after shooting once, you'll respin the barrel and then it will land on another random spot, and then maybe you shoot again, and if it's blank twice in a row, you survive. Okay. So the 2 choices are either pull trigger twice in a row, or pull trigger once and then respin and pull the trigger again. Okay. So before computing anything, I want you to see what your gut instinct says. Do you think your survival chance is better if you pull the trigger twice in a row, or you respin? Try to think about that, and we'll get to it. So it'd be nice if you can do like a random experiment to kind of simulate this, not with actual bullets or anything. But if you have like a deck of cards, right? So if you have, let's say, regular deck of cards and have 6 cards pulled out, and maybe 2 of those cards in a row are in red, and then the rest is in black. And what you could do, so imagine this is the barrel of the gun. You will face it away from you, and then you start shuffling from top to bottom. Enough time so you kind of forget where the bullets are, and then try to see if you pull out the card on the top. If it's a miss, you could either pull the next one, so that simulates pulling twice in a row. So if you draw 2 black cards in a row, you survive. Or you shuffle, and then let's say you draw one. In this case, the first bullet fired, so you lose. Let's try again. You shoot, and then maybe you die again. Maybe I haven't shuffled enough, so this time it should be blank. You get a blank, and then instead of looking at the next card, you keep shuffling, and you try again to see if you could survive 2 draws. Right, so this would be a survival. Okay, so I hope you have playing cards in your house, so you could try that. Or if you have index cards, you could just mark 2 of those X's and then the rest blank, and do similar thing with index cards as well. So what I want you to do is somehow find these kinds of replacements and see if you can try both strategies. So maybe first try to do 2 cards in a row and see what your survival rate is. Try that game 5 times. Then try look at 1 card, reshuffle, and then look another card again and see what your survival rate is with that try. If you get a red card at the beginning, then you fail the whole try. But if you get to the second stage, you could try out the 2 different strategies. And then after that random experiment, I want you to see if you change your mind or not. Maybe I should encourage you to pause the video now and see if you have cards or something that you could use to try out this game. Okay. So to really analyze which strategy is better, we have to learn a little bit about how to compute probabilities. The back side of this worksheet, or I guess there's 2.5 pages, I walk you through how to compute certain types of random experiments. So the first thing is about computing uniform probabilities of equal probable events. So if you have a trial where each of the outcomes are equally likely, so for example, with this Russian roulette example, when you spin the barrel, each of the chamber being on the top should be equally likely. So each should be 1 in 6 chance. So when you have a situation like that, there's a formula you can use to compute the probability, and it's highlighted. Formula is how you can compute them. Basically, it's going to be a fraction of where you count the number of outcomes of the outcome event A. So maybe A is the event that the bullet is not fired. And then you can divide by the number of total possible outcomes there are. So if they're equally likely, then this ratio should give you the probability of some event A happening. Just to try out this idea, I want you to try the following 3 problems. So rolling an odd number out of 6-sided die. So there's 6 outcomes in the sample space, and there are 3 outcomes in this event of rolling an odd number. And try to see if you can compute the probability. The next problem involves 2 coin tosses. So there's 4 possible equally likely outcomes. It's heads, heads, tails, tails, heads, and tails, tails. And one last one, being born on a weekend. So I think it's reasonable to assume people were born equally likely on any of the 7 weekdays. So weekend would be 2 out of those 7 days. Okay, So I want you to pause the video now and see if you can finish these computations here. And then after that, we'll move on. Okay. So another idea that's helpful when we compute things is the idea of independent events. So if you have two random experiments happening that are separated by either space or time, they don't influence each other, then they're called independent events. And if you have two independent events, then the probability that they both happen is going to be the product of the probability of each event happening. So for example, an example could be flipping two coins. The first flip and the second flip is independent. It should not influence one of them being heads or tails, does not influence if the second toss is heads or tails. So if this is a fair coin, for example, probability of getting both heads should be 1/2 times 1/2, and it'll be 1/4. Even if it's biased coin, where it's heads 2/3 of the time, the two flips are still independent. It'll be 2/3 times 2/3. Okay, so that's for two independent events to happen both at the same time, right? So this is A and B type of situation. There's a different formula for probability of two independent events, A or B or both happening. When you have an or situation, the formula you use to compute is probability of A plus probability of B minus the probability of both A and B happening. So you subtract the product of those two things. If you're wondering where this formula came from, I think it's best to see in Venn diagram. So you can kind of think of the area in this Venn diagram as probabilities. So what we want to compute is probability of A or B or both. So that's this shaded portion. So the probability of A is given by this area, and probability of B is given by this area. And when I shade those two things in, maybe you could see that, maybe this is difficult, maybe I should change the color. This intersection area was counted twice, right? So if I add probability of A and B, you have overcounted the area by the blue shaded region because you counted that area twice. So what you do is you subtract the area of A and B happening. So that's this formula. So you plug that in and you subtract the overcounted area. So you added that twice, so you subtract one and you get the exact area that you want. So that's how you can compute and or situation with independent events. You have to have the two events be unrelated, or not unrelated, but maybe does not influence each other for this formula to hold. So once, just to practice these two formulas, maybe you can try out the next three problems. So two tails or two heads in two coin tosses. So this is an or situation, so try to use the second formula. two people both born on a Monday. So this would be both being born on the same day. So this is the and situation. So you'll use the first formula. And then at least one or two people born on a Monday. So one person or the second person or both. So that's the second formula again. Okay. So I encourage you to pause the video and see if you can fill those three things out. And after practicing those things, maybe you're at a point where you can analyze the survival probabilities for the Russian roulette game. So I want you to try to compute the probability for survival for the two consecutive trigger pulls in a row, and also in the situation for you shoot once, you rotate the barrel and shoot again. So try it out, and if you can figure it out after a pause, I can help you out on how to compute the two situations. So try it first. Okay, so let's compute the probability for two trigger pulls in a row. So if you have 6 chambers and 2 of the chambers are loaded with bullet. So let's say you spin just once and you pull the trigger twice in a row. So there's 2 out of 6 chance that you hit the bullet right off the bat. So you will survive the trigger pull if you landed on one of these 4 spots, 3, 4, 5, or 6. And after the trigger pull, each chamber moves on to the next stop. Okay. So what would happen is that if out of these 4 spots, right, as long as you're not in a chamber where the next spot is the bullet, you will survive the second trigger pull. So if you landed on 3, 4, or 5, you will survive 2 trigger pulls in a row. If you landed on 6, then you pull the trigger twice. The first trigger pull is okay, but the next one will be a chamber with bullet in it. So then that would be bad, right? So out of the 6 chambers, 3, 4, and 5 is the survival spots you can land in. So 3 chambers out of 6 possibilities, or if you reduce that with the 2 trigger pulls, 50% of the time, you'll survive. If you decided to pull the trigger and then respin and pull the trigger again, this is kind of like 2 independent events, right? So with the first trigger pull, 2 out of the 6 chamber has bullet in it. So actually, if you're trying to compute for the probability of survival, there's 4 out of 6 chance that you'll survive the first pull. And if you survive this and then you respin, that's kind of like flipping the coin again, right? It's an independent trial again. And in 4 out of 6 times, you'll survive the second trigger pull. So that's kind of like 2/3 times 2/3 by just reducing the fractions, or 4/9. That would be the chance of a survival. So this is a little bit less than 50%. It's 0.4444 repeating. So chance of the survival would be 44.4%. For the respin, and then chance of survival is 50% for 2 trigger pulls in a row. I hope that made sense. In your homework, there's a similar problem that involves 7 chambers instead of 6. So if the situation changes, the probability also changes. So see if you can mimic this line of reasoning to compute which is the better situation. This problem is kind of tweakable. So in a future quiz, maybe I could give you a different situation where maybe the bullets are not contiguous spots. That changes the problem. Or maybe there's different number of bullets or different number of chambers. So see if you can understand the method well enough so you can compute other situations as well. Anyway, that's it for today. I will see you guys next week.